So the second of our 6 application models in this series of videos is on project selection. The template for the textbook example is also contained within the readings subfolder of the 05 underscore integer underscore OPT folder, just like the browser services for the workforce scheduling. Although I'm not going to go through any of those 8th chapter 15 exercises in either videos or classes, they're great examples you should do on your own as part of your chapter readings. So the textbook's example here, a couple of bullets, is on hand engineering, I guess, which is faced with a decision on which among 5 projects to select in order to maximize the project or projected rather return while staying within the given budget and personnel constraint. This is a standard example of the use of binary variables, where 1 represents the project selection and 0 project's rejection. A variation on the model includes a situation where the projects are connected. For example, selecting project 1 means, or could mean, project 4 must also be selected. Table 15.2 on page 526, which is towards the end of this example, shows several examples of how to build logical constraints into Excel without using the if function, which makes the problem nonlinear and non-smooth, which we'll elaborate on later on. Okay, and we will use these, or this particular table that I'm referencing here, again 15.2 page 526, extensively in class and for the assignment on chapter 15. So please check out these pages 524 through 527 for details on this example, as well as the logical constraint building. Okay, here at the bottom we have our own example of a project selection model, which is very similar to hand engineering, with more projects to select from, but with only a total budget constraint restriction. Okay, so I'm going to open the elect5 underscore project underscore selection that I have right here. Zoom in, show the budget of 15,000, 7 project with investment costs, NPV, and NPV per investment dollar. Okay, so we could start right by selecting projects 1, 2, and 4, I believe, because they have the highest NPV per investment dollar. Okay, so the budget, right? So the rest, let's assume are rejected or not selected, right? So then the sum product on the budget constraint, right, would take the investment cost here and multiply it with the investment decision or project selection decisions, right? And add up to $13,500, which is within the budget of $15,000. The total NPV is a similar sum product of the NPVs with the project selection or rejection decisions, yielding the total of 43,500, right? So save that. So the question now is whether there's a better combination of project selection / rejection, right? That is still within the budget of 15,000, because this obviously is a little bit of cushion here left, but that yields a higher NPV than this 43,500 shown here. Okay, so we set up the solver by going to the solver window, and then we're going to maximize the NPV B18. Okay, and we're going to change the variables, right? Decision variables are the selection rejection cells, okay, which are also constrained to be binary, for which you select the bin option in the drop down. Okay, and then there's a simple normal constraint that the amount invested has to be less than or equal to the amount of budget available. Okay, well, again, in this case, actually, it does not matter whether you make the unconstrained variables non-negative. We'll just keep it, since I think they're all checked. But make sure you check or select LP quadratic and then solve it. So you will notice, all right, that after you run the solver, that the project 5 was included, although the NPV per investment dollar is slightly less than project 4. Okay, so but what that did is, but it has a higher MPV value on an absolute basis, right? But because the cost increase, right, was not as high, relatively speaking, right, we are still within the budget constraint with a $500 left, but the MPV is actually higher at a 46 at its maximum value for the $6,000. So this sort of hopefully demonstrates that even for a tiny example with only 7 projects, okay, in a single budget constraint here, okay, it is not at all straightforward to find the optimal answer, right? Please note that an exhaustive search is not the way to go, since there are 2 to the 7th, right? 2 to the 7th, quickly, right? 2 caret symbol shift 6, 728 combinations of zeros and ones, which may not seem like a lot, but remember that the 2 to the x function is exponential. So with 20 projects, still a relatively small number. Okay, there's over 1 million combinations to sort of evaluate, right? Which is clearly not the way to go. Integer programming algorithms employ a specialized, procedure or method called branch and bound, which develops a solution tree and proceeds along the branches that improve the objective function, effectively cutting or pruning off the ones that cannot have the optimal solution. Okay, rather than doing the exhaustive search of million plus combinations for printed projects. This process reduces the number of possible combinations tremendously, obviously, and yields optimal solution relatively quickly, even for very large problems. Okay, so I'm going to save this example here, switch back to the presentation and pause.